Good day, everyone. The topic we will discuss are photoelectronics, lasers, and fiberoptics. And this report was prepared by Mr. Calanza, Castaño, and Ms. Dalipe. Here are the topics we will discuss in this presentation: laser lights, photoelectronics, lasers, and fiberoptics. So first, what is light? Light is a form of energy produced by a light source. It travels through vacuum and it transfers. It transferred um, by radiation in the form of electromagnetic wave. The properties of lights are it travels in a straight line. It has the properties of both wave and particle. Also, the speed of light has a approximately 30 million meter per second or 186,000 miles per second. There are two light sources. These are incandescent source and luminescent source. So first, incandescent source is a light source which produces a thermal radiation from an electrically heated filament or use heat to produce light. Also, tungsten and halogens are good material to be used as filament since it can withstand a higher temperature ranging up to 2000 Kelvin. Also, um, lastly rather, the example of incandescent source is sun, stars, a flame, and a molten metal. So next is the luminescent source. It is normally cooler and can be produced by chemical reaction. The good example for this are glow stick, glowworm, computer screen, fluorescent lights, and LEDs. Next, the two types of light models are light as waves and light as particles. Back in 1801 in England, a physicist named Thomas Young performed an experiment that showed that light behaved as a wave. He passed a beam of light through two thin parallel slits and result that alternating bright and dark bands appeared on a white screen some distance from the slit. Furthermore, the supporting details or supporting topics that we could say light as wave is the electromagnetic wave. Electromagnetic waves, including the visible lights, are made up of isolating electrical and magnetic fields. Next is the electromagnetic spectrum. The wavelength of electromagnetic radiation determines the color. All the visible light has a wavelength between 400 and 700 nanometer. Electromagnetic radiation with a shorter or longer wavelength is not visible to humans, but it exists and can be detected. So, let's go to light as particles. Light behaves mainly like a wave but can be also considered to be consist of tiny packages of energy called photons. Albert Einstein proposed that light is made of billions of small packets of energy that we now call photons. These photons have no mass, but each photon has a specific amount of energy that depends on its frequency. Also, each photon still has a wavelength, and a shorter wavelength photons have more energy. Also, according to Einstein, each photon of energy is equal to the product of Planck's constant and the frequency of photon. Next is the photons. Photon is a piece of energy. It has no mass. It moves at the speed of light and acts as particle's smallest unit of light. So, the properties of photons are all the quantum numbers are 0. It does not have any mass, charge, and they are not reflected in magnetic and electric field. It moves at the speed of light in an empty space, and they are considered virtually as particles. The photon energy is directly proportional to its frequency and inversely proportional to its wavelength. And then, the phenomenon of metals releasing electrons when they are exposed to light of the appropriate frequency is called the photoelectric effect. And the electrons emitted during this process are called photoelectrons. The phenomenon of the photoelectric effect was discovered by Heinrich Hertz back in 1887. Also, it is divided into two types. And these are external photoelectric effect and internal photoelectric effect. The photoelectric effect cannot be explained by considering light as wave. However, this phenomenon can be explained by the particle nature of light, in which light can be visualized as a stream of particles of electromagnetic energy. And also, these particles are called photons. Next is the external photoelectric effect. It refers to the phenomenon that electrons in the object escape from the surface of the object and emit outward under the action of light, which is also called photoelectric emission effect. These injected electrons are called photoelectrons, and it is important to note that this emission of photoelectrons and the kinetic energy of injected photoelectrons is dependent on the frequency of the light that is incident on the metal surface. The process through which photoelectrons are ejected from the surface of metal due to the action of light is commonly referred as photoemission. The photoelectric effect occurs because of the electrons at the surface of metal tend to absorb energy from incident light and use it to overcome the attractive forces that bind them to the metallic nuclei. And secondly, the internal photoelectric effect. It refers to the phenomenon that illumination changes the conductivity of an object or produces photoelectromotive force. It is also divided in photoelectric conductivity effect and photovoltaic effect. So, photoconductivity effect is a phenomenon that electrons absorb photon energy from bonding state to free state under the action of light, which results in the change of material conductivity. Next is the photovoltaic effect. It refers to the phenomenon that light causes potential difference between the different parts of inhomogeneous semiconductor or semiconductor bonding the metals. Also, the principles behind the photoelectric effect is the law of conservation of energy forms the basis for the photoelectric effect. Our next topic is photoelectronics. Photoelectronics materials and components. Under the photoelectronic materials are optical glass, optical plastic, optical crystals, infrared materials, laser materials, semiconductor optoelectronic materials, and electrical materials, and etc. Under the photoelectric components are light emitting devices, light detecting or receiving components, light conduits, and phototransistors, solar etc. So, the photoelectric materials are the foundation and the pioneer of the whole photoelectric industry. It refers to the materials can be generated, convert, transmit, process, and store optical signals. They mainly include semiconductor photoelectronic materials, organic semiconductor photoelectric materials, inorganic crystals, and quartz glass. Compound semiconductor materials such as aluminum, gallium arsenide and indium gallium arsenide nitride can be formed by any combination of group 3 to group 5 elements. Their lattice constant, bandgap width, and absorption or emission wavelength are the three most important parameters determining the photoelectric properties of compound semiconductor materials. And the good example of elements can be used are silicon, cadmium telluride, gallium arsenide, and copper indium diselenide. Next is the photoelectric components or devices. It refers to the devices that can realize the conversion function between light, radiation energy, and signal, or the transmission, processing, and storage of photoelectric signals. At present, most commercial semiconductor optoelectronic devices are made of gallium arsenide base or indium phosphide base and gallium nitride um, based compound semiconductor material systems. They are widely used in optical communication network, photoelectric display, photoelectric storage, photoelectric conversion, and photoelectric detection. And these are categorized into two classes. First is it generates electricity on exposure to light. For example, photoemissive and photovoltaic devices. And secondly, it conducts electricity on exposure to light. Example, photoconductive or photoresistive and photojunction devices. Next is the phototransducers, and there are four primary types. These are photoemissive cells, photoconductive cells, photovoltaic cells, and photojunction. For the photoemissive cells, this electron emission due to incident radiation upon photoemission surface, and it is also known as phototube. There are three basic types of phototube. These are vacuum phototube, gas-filled phototube, and photomultiplier phototube. First, the photovacuum phototube consists of rod anode, curvature cathode in a vacuum glass. Cathode is coated with emissive material and emits electron when light radiation occurs on them. Secondly, the gas-filled phototube. Same construction as the vacuum phototube except the presence of inert gas, or also known the argon gas, into the tube. And the third type is the photomultiplier tube. It consists of evaluated glasses. Consists of evaluated glass envelope containing photocathode, anode, and dinodes. Electrons emitted by the cathode are attracted to the first dynode and emitted again to the following dynodes. Next, we have photoconductive cells, and the example is the photoresistors. It is fabricated from a semiconductor material such as cadmium sulfate, cadmium selenide, and the increase of current with light intensity while the voltage remains constant makes the resistance of semiconductor decrease. Also, the photoresistor known as light-dependent resistor. It is a simple, high sensitivity, and low cost. Variation of temperature affects the resistance for a particular light intensity. For the construction of the LDR, we have the body encapsulation or housing, the photoconductive material, the electrodes, and lastly the wires for external connection. And the conductive cells consist of strips of light-sensitive material situated between two conductors. So, typical curves of resistance versus the elimination. our next to be discussed is the photovoltaic cells. These semiconductor junction devices for converting radiation energy into electrical energy, or we must say voltage. It is also known as solar cells. Before we discuss the photojunction, let's review the LED. Light emitting diode is a semiconductor device that emits light when an electric current is passed through it. LEDs are comprised of compound semiconductor materials, which are made up of materials such as gallium arsenide and gallium phosphide. LEDs operate by the electroluminescence, a phenomenon in which the emission of photons is caused by electronic excitation of material. So, we have the photojunction, and in the photojunction we have two kinds, and these are photodiodes and phototransistor. The photodiodes is a silicon diode with the lens on its case to focus the incident of light to the junction. And furthermore, the conversion efficiency depends on spectral content and illumination intensity. Without a bias, it operates like a photovoltaic device or voltage source. And when reverse bias, it operates like a photoconductive device. The important advantage is it is a fast response compared to the photoconductive device, and it is also small and inexpensive. Here is the table. We compare the LED and photodiode, and the basis of the comparisons are the function, operation mode, working mechanism, fabrication, temperature change, light, current leakage, working principle, and application. Next is the phototransistor, a NPN device by addition of junction to photodiode. It provides the large amount, or rather output current compared to the photodiode for a given amount of illumination and very small area. It is more sensitive than a photodiode up to factor of 100. Optooscillator, a device where transistor and a light-emitting diode may be combined in a single envelope. In this case, the LED provides the source of illumination to which the phototransistors react. It can be used in two working modes, either as a photodiode with the emitter of the transistor or as phototransistor. Furthermore, in both cases, the operation is governed by the current flowing to the LED section. Further variation on this device are the opto-Darlington isolator and opto-Triac isolator. The former comprises typically and optically coupled gallium arsenide. The former. Next is phototransistor, NPN device. Next is phototransistor, a NPN device by addition of junction to photodiode. It provides large output current compared to photodiode for a given amount of illumination in a very small area. It is more sensitive than a photodiode up to a factor of 100. Optoisolator, a device where phototransistor and light-emitting diode may be combined in a single envelope. In this case, the LED provides the source of illumination to which the phototransistor reacts. It can be used in two working modes, either a photodiode with the emitter of the transistor or phototransistor. In both cases, the operation is governed by the current flowing through the LED section. Further variation on this device are opto-Darlington isolator and opto-Triac isolator. The opto-Triac isolation is essentially similar with the a triac replacing the transistor pair and capable of being worked directly from household AC voltage.
Our next topic is laser, or light amplification by stimulated emission of radiation. The theoretical basis for the development of laser was provided by Albert Einstein in 1917. In 1960, the first laser device was developed by Th. Meinman. Stimulated absorption. Let E sub 1 and E sub 2 be the energies of ground and excited states of an atom. Suppose, if a photon of energy E sub 1 minus E sub 2 is equals to Hv interacts with an atom present in the ground state, the atom gets excitation from ground state E sub 1 to excited state E sub 2. Stimulated absorption rate depends upon the number of atoms available in the lowest energy states as well as the energy density photons. Stimulated absorption rate is directly proportional to the number of atoms in the ground state is directly proportional to the density of photons. Spontaneous emission. Spontaneous emission was postulated by Bohr. Let E sub 1 and E sub 2 be the energies of ground and excited states of an atom. Suppose, if a photon energy E sub 1 minus E sub 2 is equals to Hb interacts with an atom present in the ground state, the atom gets excitation from ground state E sub 1 to excited state E sub 2. The excited atom does not stay in a long time in the excited state. The excited atom gets the excitation after its lifetime by emitting a photon of energy E sub 1 minus E sub 2 is equals to Hb. This process is called spontaneous emission. The spontaneous emission rate depends upon the number of atoms present in the excited state. Spontaneous emission rate is directly proportional to the number of atoms in the excited state. The stimulated emission was postulated by Einstein. Let E sub 1 and E sub 2 be the energies of ground and excited states of an atom. Suppose, if a photon of energy to be excited state E sub 1 minus E sub 2 is equals to Hv interacts with an atom present in the ground state, the atom gets excitation from ground state E sub 1 to excited state E sub 2. Let a photon of energy E sub 1 minus E sub 2 is equals to Hv interacts with the excited atom within their lifetime, the atom gets the excitation to ground state by emitting of another photon. These photons have same phase and it follows coherence. The phenomenon is called stimulated emission. Stimulated emission rate depends upon the number of atoms available in the excited state as well as the energy density of photons. Stimulated emission rate is directly proportional to the number of atoms in the excited state and directly proportional to the density of photons. The given table is the summary of the spontaneous emission and stimulated emission. Characteristics of lasers. Highly directional. The light ray coming from ordinary light source travels in all directions, but laser light travels in single direction. For example, the light emitted from torchlight has a given distance, but the laser light spreads a few centimeters distance even it travels lakhs of kilometers distance. The directionality of laser beam is expressed in terms of divergence, where angle of change is equals to r sub 2 minus r sub 1 over d sub 2 minus d sub 1. R sub 1 and r sub 2 are the radii of laser beam spots at distance of d sub 1 and d sub 2 respectively from laser source. Highly monochromatic. The laser light is more monochromatic than that of a conventional light source. This may be due to the stimulated characteristics of laser light. The bandwidth of conventional monochromatic light source is 1000 Armstrong, but the bandwidth of ordinary light source is 10 Armstrong. For high-sensitive laser source is 10 raised to negative 8 Armstrong. Highly intense. Laser light is highly intense than the conventional light. An 1 milliwatt helium and neon laser is highly intense than the sun intensity. This is because of coherence and directionality of laser. Suppose when two photons of each amplitude A are in a phase with other, then Young's principle of superposition. The resultant amplitude of two photons is 2A and the intensity is 4A raised to 2. Since in laser, many numbers of photons are in phase with each other, the amplitude of resulting wave becomes NA, and hence the intensity of laser is proportional to n raised to 2 A raised to 2 So, 1 milliwatt helium neon laser is highly intense than the sun. Highly coherence, a predictable correlation of the amplitude and phase at any one point with other point is called coherence. In case of conventional light, the property of coherence exhibits between a source and its virtual source, whereas in case of lasers, the property coherence exists between any two or more light waves. There are two types of coherence. One is temporal coherence and two is spatial coherence. Temporal coherence, the predictable correlation of amplitude and phase at one point on the wave train WRT, another point on the same wave train. Then the same wave is said to be temporal coherence. To understand this, let us consider 2 points P sub 1 and P sub 2 on the same wave train, which is continuous as in shown in figure 1. Suppose the phase and amplitude at any one point is known. Then we can easily calculate the amplitude and phase for any other point on the same wave train by using the wave equation. The given formula in temporal coherence, where A is the amplitude of the wave and x is the displacement of the wave at any instant of time t. Spatial coherence, or also known as transverse coherence, is the predictable correlation of amplitude and phase at one point on the wave train WRT, another point on a second wave. Then the waves are said to be spatial coherence or transverse coherence. There are two waves are said to be coherent. The waves must have same wavelength and same phase. Population inversion, the redistribution of atomic energy levels that takes place in a system so that laser or maser action can occur. Normally, a system of atoms is in temperature equilibrium and there are always more atoms in low energy states than in higher ones. Absorption and emission of energy is a continuous process. The statistical distribution of atoms in the various energy states is constant. When this distribution is disturbed by pumping energy into the system, a population inversion will take place in which more atoms will exist in the higher energy states than in the lower. There are 5 different types of lasers: solid lasers, liquid lasers, gas lasers, dye lasers, semiconductor lasers, and their corresponding examples. One of the pioneer lasers is ruby lasers, which has a 3-level solid-state laser and was constructed by Mainman in 1960. In constructing ruby lasers, the rod is generally used 4 cm length and 5 mm diameter. Both the ends of the rod are highly polished and made strictly parallel. The ends are silvered in such a way one becomes partially reflected and other end fully reflected. The ruby rod is surrounded by xenon flash tube, which provides the pumping light to excite the chromium ions in the upper energy levels. Xenon flash tube emits 1000 joules of energy in few milliseconds, but only a part of that energy is utilized by the chromium ions while the rest energy heats up the apparatus. A cooling arrangement is provided to keep the experimental setup at normal temperatures. The working states of ruby lasers, where its energy level diagram of chromium ions is shown in figure. The chromium ions gets excitation into higher energy levels by absorbing of 56,000 Armstrong of wavelength radiation. The excited chromium ion stays in the level H for short interval of time, 10 raised to negative 8 seconds. After their lifetime, most of the chromium ions are de-excited from H to G, and a few chromium ions are de-excited from H to M. The 3 disadvantages or drawbacks of ruby lasers. First, the laser requires high pumping power. Second, the efficiency of ruby lasers is very small. Third, it is a pulse laser. Uses of ruby lasers. First, use in optical photography. Second, used for measurement of plasma properties such as electron density and temperature. Third, used to remove the melanin of the skin. Fourth, used for recording of holograms. Helium neon lasers. where ruby lasers is a pulse laser, even it have high intense output. For continuous laser beam gas lasers are used. Using gas lasers, we can achieve highly coherence, high directionality, and high monochromicity beam. The output power of the gas lasers is generally in few milliwatts. The first helium neon gas lasers was fabricated by Ali Havan and others. How helium neon laser works. When the electric discharge is passing through the gas mixture, the electrons accelerated towards positive electrode. During their passage, they collide with helium atoms and excite them into higher levels. F sub 2 and F sub 3 form F sub 1. In higher levels, F sub 2 and F sub 3, the lifetime of helium atoms is more. So there is maximum possibility of energy transfer between helium and neon atoms through atomic collisions. When helium atoms present in levels F sub 2 and F sub 3 collide with neon atoms present ground state E sub 1, then neon atoms gets excitation into higher levels E sub 4 and E sub 6. As follows, due to the continuous excitation of neon atoms, we can achieve the population inversion between the higher levels E sub 4, quantity E sub 6, and lower levels E sub 3, quantity E sub 5. The various transitions, E sub 6 going to E sub 5, E sub 4 going to E sub 3, and E sub 6 going to E sub 3 leads to the emission of wavelengths 3.39 micrometer, 1.15 micrometer, and 6,328 Armstrong. The first two corresponding to the infrared region, while the last wavelength is corresponding to the visible region. The neon atoms present in the E sub 3 level are de-excited into E sub 2 level by spontaneously emitting a photon of around wavelength 6,000 Armstrong. When a narrow discharge tube is used, the neon atoms present in the level E sub 2 collide with the walls of the tube and get de-excited to the ground level E sub 1. These are the following fields that we can apply lasers: communication, computers, chemistry, photography, industry, medicine, military, and lastly, scientific research. The table shows the specific applications of lasers for each fields.
Our next topic is all about fiber optics. So what is fiber optics? An optical fiber is a thin, flexible, transparent fiber that acts as a waveguide or light pipe to transmit light between the two ends of the fiber. Optical fibers are widely used in fiber optic communications, which permits transmission over longer distances at a higher bandwidth data rates than other forms of communication. Fibers are used instead of metal wires because signals travel along them with less loss and are also immune to electromagnetic interference. For the evolution of fiber optic systems, so we have 5 generations, and the first generation is, it said that the bit rate is 45 Mbps, the repeater spacing is 10 km, and also in the second generation is the bit rate is 100 MB per second to 1.7 gigabytes per second and also the repeater spacing is 50 km. For the third generation, the bit rate is 10 gigabytes per second, the repeater spacing is 100 km, and for the fourth generation is the bit rate is 10 terabytes per second and the repeater spacing is 10,000 km. And lastly, for the fifth generation is the bit rate is 40 to 160 gigabytes per second and the repeater spacing is 24,000 km to 35,000 km. Element of an optical fiber transmission link. Basic block diagram of optical fiber communication system consists of following important blocks. So we have the transmitter, information channel, and the receiver. So in the transmitter, we have first the modulator, carrier source, channel coupler, and after that we goes to the information channel, which we have the fiber optic cable which is interconnected with our repeater to receiver. So under the receiver, we have the optical detector, next is the amplifier, and next is the processing and that goes the message output. Fiber optic cable consists of 4 parts. So these 4 parts are the major parts of fiber optic cable. So first we have the core, second is cladding, third is buffer, and fourth is jacket. So the thickness of jacket is 400 micrometer, the buffer is 250 micrometer, the cladding is 125 micrometer, and lastly the core is 8 micrometer. So here are the definition of 4 parts. So first, the core. The core of a fiber cable is a cylinder of plastic that runs along the fiber cable's length and offers protection by cladding. Second is cladding. Is an outer optical material that protects the core. The main function of the cladding is that it reflects the light back into the core. Next is the buffer. The main function of the buffer is to protect the fiber from damage, and thousands of optical fibers arranged in hundreds of optical cables. And lastly, the jacket. Fiber optic cables jackets are available in different colors that can easily make us recognize the exact color of the cable we are dealing with. The color yellow clearly signifies a single-mode cable, and orange color indicates multi-mode. In consideration, we have the types of optic fiber based on core materials. So first, we have the glass fiber, and the second is plastic fiber. In the glass fiber, the core and cladding of the optical fiber are made of glasses. So in the plastic fiber, the core and cladding of the optical fiber is made of plastic. Classification based on mode of propagation. So we have 2 types of classification. First is the single mode fiber, and the second is multi-mode fiber. So in the single mode fiber is the core diameter of the single mode fiber is small, and light can travel a longer distance with smaller refraction. And in the multi-mode fiber is it has a larger core diameter than that of single mode fiber optic cable, which allows multiple pathways and several wavelengths of light. So as you can see here in our diagram below, so multi-mode fiber is greater than the single mode fiber in diameter. So in our multi-mode fibers, we have the 50 micrometer, and the single mode is 9 micrometer. Types of optic fiber based on refractive index. So we can see here the diagram below, and it is a monomode optical fiber. So it has a very narrow core of a diameter about 5 meter or less. Cladding is relatively big. Second is multi-mode optical fiber. It is again of 2 types. First is step index multi-mode fiber. The diameter of the core is about 50 micrometer. The core has a constant R. The refractive index then changes to a lower value, which remains constant through the cladding. Second, graded index multi-mode fiber. Refractive index decreases smoothly from its center to the outer surface of the fiber, which is cladding. There is no noticeable boundary between core and cladding. Characteristics of fiber. First is wider bandwidth. The optical carrier frequency is in the range of 10 raised to 13 Hz to 10 raised to 15 Hz. Second is the low transmission loss. The fibers are having a transmission loss of 0.002 decibel per kilometer. Third is the dielectric waveguide. Optical fibers are made from silica, which is an electrical insulator. Therefore, they do not pick up any electromagnetic wave or any high current lightning. Fourth is the signal security. The transmitted signal through the fibers does not radiate. Further, the signal cannot be tapped from a fiber in an easy manner. Fifth is small size and weight. Fiber optic cables are developed with a small radii, and they are flexible, compact, and lightweight. The fiber cables can be bent or twisted without damage. Operation of optical fiber. First, a hair-thin fiber consists of 2 concentric layers of high-purity silica glass, the core and the cladding, which are enclosed by a protective sheath. Second is core and cladding have different refractiveness indices, with the core having a refractive index N1, which is slightly higher than that of the cladding N2. Third is it is this difference in refractive indices that enables the fiber to guide the light. Because of this guiding property, the fiber is also referred to as an optical waveguide.